Okay, good day everyone. So this is a sort of correction video, no, for the uh, video I just uploaded about gating design. In a portion of that video, I mentioned that the numerator A here pertains to the upstream area, and I'll also timestamp that particular section. No? You can check the video out. But in any case, I mentioned that the numerator A here refers to the upstream area, while the denominator refers to the downstream area, for which the change have been accounted for. No, and this is true. No, but I've erroneously stated that the upstream area refers to the immediate area before the accounted change was observed. But it's not. That is where the error is. No, because the upstream area will always be the choke area. So take into account or let's remember again that the choke area is the main control area. Ev- uh, Therefore the upstream area should always be the choke area for this particular case. Okay, so the original equation was correct, no? That the numerator here refers to the choke area, and this is true for all instances of the loss coefficients. So again, I've mentioned in the previous video that if you have and the problem with this hydraulic efficiency factor is that this C value is needed uh, for us to be able to solve the choke area, but we also need the choke area so that we can solve for the hydraulic efficiency factor C. So it becomes a circular reference, no? So the way we go about it is establish the gating ratios first. So I've also discussed gating ratios in that previous videos. So again, just to refresh your memories, gating ratios is expressed as the ratio of the choke area versus the runner areas, the total runner areas, as I should say, and the total in-gate areas. Okay, so if you have something like a gating ratio of 1:3:3, then we can solve for the hydraulic efficiency factor without actually finding the exact value for the choke area. Okay, so let's just take an example. No, if we have, for example, a down sprue, we have a sprue and it's going or it's running from that down sprue into a bend running into the runner. Then we have the first area here is the choke area, and it is running into the the runner area, the runner cross sectional area. So if we know the gating ratio, then we can say that the runner area, and let's just take this for example, no, the runner area is just equal to 3 times the choke area. Again, the assumption here is that we only have one runner, and since this is one runner, then the total cross-sectional area in this particular gating ratio is equal to the individual runner area. But again, if we have uh, something like this, where the sprue splits into two sections, then the individual runner area will be equal to the total runner area divided by the number of runners. So in this particular case, this runner area here will be equal to 3 halves uh, AC over AR. Uh, 3 half 3 halves times the choke area, I should say. Okay, so let's take the example again. So let's just simplify it now, and we have a runner area, a single runner from that down sprue, then we should have, if we were to establish this gating ratio, we should have that the running area is equal to just 3 times the choke area. So if you take this term, we can simplify this term as a over a1 squared. And since we know the gating ratio, then this will just be equal to uh, AC over 3 times AC. where again the runner area is just 3 times AC. So this cancels out, and we have 1/3 squared. Okay, so with that, we can solve for the hydraulic efficiency factor, and we'll use that hydraulic efficiency factor to solve for the effective choke area. Okay. So one of the erroneous statements I made another one of the erroneous statements I made during that particular segment that I've time stamped in that video is that when we have a directional change, no? So for example, if we have something like this is the top view, kunwari, this is the top view, and let's just say this is the sprue, the down sprue seen as in the top view, and it's running through a runner, and the runner has a directional change. So again, any change must be accounted for in the loss coefficient, whether that change is a change in area or a change in direction. Okay, so if it's running through this value, through this particular channel, then this is your runner area, and this is also the runner area now. So I said that the loss coefficient term associated, or the loss contribution uh, to the efficiency factor for that particular case is equal to the K multiplied by AR over AR, and this cancels out to 1. That's what I said in the video now. And again, this is erroneous because the numerator will always be the choke area, no? So in the correct way of solving this should be the loss coefficient for a bend, and for that bend, we can look at the table now. It's We can see that a right angle bend in a runner, and let's just assume this is a square cross section, is 2. So the we can have a loss contribution of 2 times the choke area divided by the runner area. So again, the numerator will always be the choke area. Okay, so that's all for the correction. So it's a short correction video, no? And to give you, I said that I'll give some more examples for calculating the hydraulic efficiency factor, and I can do it in this video as well, no? Okay, so to give you a better understanding of how to use the hydraulic efficiency factor equation, let's try this sample problem, no? So shown below is a top view of a gating system for an aluminum casting, and if a gating ratio of 1:4 is to 4 is to be used, we are to calculate the hydraulic efficient factor C, and it is noted that rounded corners are permitted for this casting. Okay, so to begin, we'll first calculate the individual runner areas and the individual gating areas, or ratios, I should say. No? So we have a gating ratio of 1:4 is to 4. And we note that from this sprue, we have 2 runners, one runner going to this end and another runner going into this end. Okay, tap, and after that, each of the runners have 2 in gates connected to them, giving us a total of 4 in gates. So we have one in gate 1 here, in gate 2, we have in gate 3, and in gate 4. Okay. So we know the gating ratio, it's 1:4 is to 4. So first, let's compute for the individual runner area. So the individual runner area, and the assumption here is that the runner area here is equal to the runner area here. Same goes for the in-gates, no? This in-gate area here is equal to this in-gate area here, and here as well. Okay? So if the gating ratio is 1:4 is to 4, then our runner area, this is the total runner area, is equal to 4 times the choke area. So that's 4 times the choke area AC. But since we have 2 runners, then we divide it by 2, giving us 2 AC. meaning that each of the individual runner areas is equal to twice that of the choke area. Okay, so again, I'll just note that this is individual runner area. Okay, so again, class, the gating ratio is the ratio of the choke area versus the total runner area versus the um, total in-gate area. Okay, so if you want to compute for the individual areas, you need to divide it the total uh, by the number of runners and in-gates that are available in the system. Okay, so if we compute for individual in-gate, this is equal to uh, 2 times, no, sorry. This is equal to 4 times the choke area because it's 1 is to 4 is to 4. And we divide it by 4 in-gates, available in-gates. That becomes AC. So meaning that the in-gate area is just actually equal to the choke area. Okay. So now that we have that, we can now take into account all of the different changes that occur as the metal goes through the different channels now. So we start with the down sprue. So the down sprue, it starts here, and from the down sprue, the metal goes into two separate channels now. So let's take into account those two changes. So the first change, and I'll just place my working equation here now. So that's the hydraulic efficiency factor C is equal to 1 over square root of, and let me just check the formula. It's 1 plus the different coefficients now. So that's 1 plus, let's take into account the first coefficient. So this is the first change. Let's just say this is the first change, this is the second change. Okay. So we have K1 here. This is a bend from sprue to runner, and if you look at the table, the right angle bend in or the bend of sprue into runner is equal to 2 for sharp and 1 for round. And since the problem states that we can use rounded corners, then we use the rounded values now. Okay, so the bend of sprue into runner is 1. So we have 1 times the choke area divided by the runner area. Okay, so again, this runner area is equal to 2AC. 2A, this cancels out. And we have another area here that is our second change, which has the same value. So that's 1. This is the loss coefficient, 1 multiplied by A over 2A. Sure. Okay, so we've taken that into account. Now the next coefficients we need to take into account is this one. This is a right angle bend. So again, changes, it could be a change in area, it could, or it could also be a change in direction. So that's, we've changed it from going this way, it makes a right angle turn, going that way, and also in this direction as well. So let's consult our table again. And if you look at the table, a right angle bend in the runner, and the problem does not state the, I don't know, what type of gating system we are using. And so let's just assume that we are doing um, a square cross-sectional area. So assuming that this is a square cross-sectional area, so a right angle bend in runner for a rounded corner. Again, the system allows rounded corners. Therefore, we use 1.5. Okay, so we have 1.5 multiplied by, let's just extend this one. That's That's 1.5 multiplied by the choke area. Again, the numerator is always the choke area divided by the runner area, which is our runner area is 2 times AC. So again, cancels out. We have So another or some tips in doing this equation, we can actually so that we won't so that it is not necessary to write uh, the variable a all over again. No, we can actually have instead of doing this, we can have AC over AR ratio. So the AC over AR ratio for this particular case is equal to 1 over 2. Okay, and this one it's equal to AC over AR is just equal to 1, so that we will not have to write A all the time now. Okay, so that's a right angle bend. Then this is for the third one, and the fourth one is on the other side. So we'll just do the equation again now. So that's 1.5 times the ratio 1 over 2 squared. Okay, so the next the encounter change encounter is when from the runner it goes into the in gates. Okay, so this is the fifth, sixth, seventh, and eighth. Okay, so we'll have in total eight loss contributions now from the different changes. So let me just extend this again. And for this one, since 5, 6, 7, and 8 all have, we are assuming that they are equal in area and they are analogous with each other. No? So we can just say plus 4 times whatever value will calculate. Okay. So in fact, we could have also done, instead of doing these two, we could have just done 2 times 1 half squared, something like that. Okay. Just to save us some space when we're doing um, the solution. Okay, but in any case, let's do this now. So we let's take into account this one. So let's consult our table again. So this is actually a junction at right angles to the runner, no? So this could either be this one or this one. Okay, but there is a distinction between these two, no? If it's a junction at a right angle to runner, then we can just use the first one, which is 4 to 6. But if it's a junction with 25% or more area reduction from the runner into the in gate, then we should use um, a value of 2 or 0.5 if it's rounded corner. Okay. So we note that if you look at it, no, the junction here is a right angle one, and the area of the in gate versus the area of the runner is actually just one half of the runner, no? Because the in gate is equal to the choke area as given by this ratio here, no? The in gate, oh no, sorry, this is supposed to be in gate. No? So the in gate, I or G, you can use I or G since it's gate or in gate. So the area of the in gate is equal to the area of the choke, but we know that the area of the choke is equal to one half the area of the runner. So meaning that the area of the runner is equal to twice the area of the in gate. Okay? Meaning that there is a 50% change in the area. So from a large, this is saying that you have a large in gate, a large runner area, and it's moving into one half its original area, okay, into the in gates. So with that, it satisfies this condition, no? With 25% or more area reduction. So we actually have a 50% area reduction, no? So this becomes, so we can use um, this gate element, no? So we have 0 0.5, again, rounded corners, 0 0.5. So we have plus 4 times 0 0.5 multiplied by the in gate to choke area ratio is just 1, no? 1 squared. Okay. So with that, we can use MS Math or we can use our calculators to solve this. And let me just open up my Microsoft Math now. So let's do 1 over square root. Square root of 1 plus 1 times 1 over 2 squared. And we multiply this by 2 plus 1.5 times 1 over 2 squared. Again, multiply this by 2 plus 4 times 0.5 times 1 squared. Okay, and if we evaluate it, we get a value of 0.48. That is our hydraulic efficiency factor for this particular case. Okay, so I hope that makes some sense. Thank you for listening to this lecture, and I'll see you in the next video.